Hi, good morning, and welcome to the ZP Developer Zone. So we like to do this Developer Zone once a week, and it's really just answering technical questions that have come in during the week. So let me sort of essentially jump straight into it. And I realise that I normally talk about the upcoming webinars that we have, or maybe the upcoming courses that we have, and I realise I've left that off. But let me jump straight into this. It's probably just worth saying that only and only if you purchase through the web store using this code in December, you'll get a 10% discount. And it's also, and that's the link to that there, so I'll put that underneath the video as well. Now, this webinar is really about answering technical questions that have come in during the week, so let me be a little bit efficient and sort of jump into it. So one of the questions is the characterization of third-party electrodes. So we've received some electrodes this week. We did some characterization on them. Now, it's no criticism of the electrodes, but we didn't get the world's greatest data. But I just want to talk about, when you don't get the great data, for example, in this case, it's cyclic voltammetry. So it'll help you sort of troubleshoot cyclic voltammetry a little bit. Somebody was watching one of our YouTube videos. We have a YouTube video that talks about really the role of, or an introduction to potentiostats. And they were kind enough to watch it, they were kind enough to like on it, and they were kind enough to then ask a question. And that question is really about IR drop. If we've got these potentiostats, and they're so good because they've got these kind of feedback loops that mean that we control the potential at the working electrodes, then why do we have an IR drop problem? And, EIS, why do we still have a problem with EIS, or electrochemical impedance spectroscopy? And I will answer both those questions. EIS is actually a good method for telling you that you have an IR drop problem and how much of it you actually have. And the feedback loop in a potentiostat is actually helping to compensate for what's happening at the counter electrode so that you control what's happening in the working electrode. But there's still an IR drop between the reference and working, and I will point that out today. Question number 3 is making an aptamer sensor. So I would say a very qualified PhD students having some problems with an aptamer sensor. I generally think the problem actually lies with the aptamer itself, as opposed to anything that they're really anything they're doing. This aptamer is binding to the gold surface, but I'm not sure that the aptamer is undergoing the conformational change that they would want. And then building a biosensor for catecholamines. These are things like adrenaline in the human body. So just characterization of third-party electrodes. I could also call this troubleshooting cyclic voltammetry, but we did some testing. In fact, in front of me, I should sort of flash this up. I have a potentiostat, and in fact, I could even do that kind of measurement that we do on electrodes shortly, in fact. But I'll go back to my actual screen and just kind of talk through what is happening here. So we were testing, and now the nice thing is we can do quite high throughput testing, and at ZP we do a lot of high throughput testing because we ship a lot of electrodes kind of like this, or there's also a 501 which has a circular design. So we're quite used to it, and we also have tools that really allow us to crunch data quite quickly. Not quite quickly. It's called Julie. You may see it sort of play out a little bit today in this webinar. But with these electrodes, we tested something like probably, I was going to say, is it 10? About 10-ish, yeah. 10 to a dozen. And we got a relative standard deviation of 10% on the peak height, and we got a relative standard deviation of 6% on the peak position. Not terrible. It's absolutely not terrible. But then I was kind of a bit curious because they're very stretched out. And this is kind of when it comes to troubleshooting cyclic voltammetry. If you see this kind of stretched out, it suggests that there's a kind of high impedance in somewhere in your measurement circuit. When I say stretched out, the kind of peak position here is approximately 350 millivolts, and the peak position here is about minus 50 millivolts. So they're stretched. They've got a peak-to-peak separation of about 400 millivolts. And ideally, an ideal situation is the peak-to-peak separation is 59 millivolts. Now at ZP, we don't try to kind of get that 59 millivolts. I'll do lots and lots and lots of webinars about that. but they didn't get, they certainly didn't get 59 millivolts. But good people, and I did want to check something, so we did actually check the impedance of the tracks. The tracks are good for definites. You know, they have low impedance, so it wasn't the tracks. And they were also kind enough to just send me the data as well. And I can see that their peak-to-peak separation is more like sort of 90 millivolts when tested at 50 millivolts per second kind of scan rate. So what does this tell me? It tells me really that, you know, and you've got to be, you know, that we at ZP may have a connection issue connecting to their screen printed electrodes. So I just want to kind of drill into that a little bit now as well. That something that we've really taken care of in many of our instruments is actual connection. So let me just show that slightly here. So this is a potentiostat from Zimmer and Peacock. Now we didn't use this configuration when we were testing our electrodes, but if I take this electrode and put it here, the nice thing to notice is there's actually no cabling. Cabling can be a real confounding problem when doing electrochemistry. Cabling, it can be long, sometimes it's unshielded, sometimes it can pick up electromagnetic kind of noise. You'll notice that actually there's no cabling here. And you'll also notice that I actually just click that in. One of the big problems with potentiostats, I think, is they put slots on them these days. So it's kind of just slotting these screen printed electrodes in. And I think that's actually a real problem because it actually allows for the ingression of liquid. But this one, I'll just take that screen printed electrode out and I'll bring this up. This one, the way it functions, we don't have a slot. And in fact, all the electronics are kind of up top here. So it's really, I wouldn't say impossible. Yeah, it is practically impossible to actually get liquid inside of this. So it really helps just in the research, but it also helps kind of in the teaching lab and things like that. And what we have here is, I'll just take this out, take this out because it's convenient to clean it then. You can see these pins here. You can see that we've got gold pins in there that make direct contact with the screen printed electrode. So on this particular model, we really take care of the connection issue. And it connects really well to our screen printed electrodes. So when I see distorted voltammetry the way I've just shown it, it makes me think, we have somewhere in this circuit there's an impedance problem, especially when this person's able to show me the CVs that they've recorded. So, you know, and so I bring it up to say, maybe I'll just slightly rewind on this. If you're expecting something that looks, when I say something that looks like this, if you're expecting something that looks elegant and beautiful like this, and you actually get something that looks like this, and then and as I say, we actually checked to make sure that the resistance tracks in the electrodes weren't actually particularly high, and they weren't. Sorry, the tracks on the screen printed electrode weren't high, and they weren't. Then it probably comes down to the connection. I may actually just do a quick demonstration. So the kind of experiment that we often do when checking on an electrode's quality or not is, I have a screen printed electrode here, I have the potentiostat here, I have the sensor or potentiostat here. So I'll take this electrode, I will click it into the unit, I'll close it, I'll take, I've got some sort of test solution that we could otherwise have purchased off the ZP website, 5 millimolar ferricyanide. I will take a aliquot of this, 50 microliters. So I'm going to put 50 microliters onto the screen printed electrode so that I can test it now, which I am now doing. I will just go to settings, I'll go continue. I'm just going to increase my current range. Whoops a daisy, that's repeats. I'm just going to increase my current range. I'll go start and off it goes. So these are doing cyclic voltammetry, and doing cyclic voltammetry is a kind of quality control on electrodes. Is not at all, I don't want to say, you know, I don't want to trivialize it, but it's not at all, well, I could trivialize it. It's not at all hard. And it's something that, you know, we definitely do quite a lot of. And as I say, in this particular case, we were doing an analysis of a third-party electrode, but we didn't get the data quality that we expected. And because it was like a new electrode to us, we didn't necessarily have put the time in on the connections, and that sometimes, you know, sort of happens. So I suspect that what we'll do then is put some engineering time in on those connections and basically make sure that, you know, that's, let's say, not the source of the problem. So I just want to show you, I'm just going to go back to my screen here, in fact, and just show you that on the app, the app finished with upload complete. So I can actually go in now. This is a very different type of, and in fact, I mentioned Julie earlier on, and Julie's a very powerful system. So whenever we make measurements at ZP, or whenever we run a potentiostat, all the data actually goes up to the cloud. So I can see that actually I've just done that CV, a very quick CV, and I can see all the data's actually up in the cloud. So if I was to summarize, if you're expecting something elegant like this, but you get something like this, and you sort of troubleshoot for a bit, and you're not quite sure what's going on, then it's probably worth checking your connections. And it's probably worth saying at ZP, actually, if people are buying screen printed electrodes off us, and they're using third-party potentiostats, we do have connectors, because we have had it that people have sort of said, oh, your electrodes are no good, and it's actually the connection that's the issue. As it is with the Sensi All potentiostat, we've put a lot of effort into making sure the connections are really good. Right, now I'm going to answer kind of a question that originally popped up on, I think, on YouTube, but then the person filled in our online form. You'll see the link for the online form in a bit, and I'll just answer their question. So potentiostats, their kind of question is really, well, if potentiostats had this feedback loop that helps to kind of control the potential at the working electrode, why do we have a problem with IR drop? Now, this is the working electrode, this is the counter electrode. Before there were potentiostats, if I wanted to oxidize ferrocyanide to ferricyanide, I could apply a potential across between these two electrodes, and, you know, I could get an oxidation, and there would be a certain amount of potential at the working electrode that would allow the oxidation potentially of ferrocyanide to ferricyanide. Now, that total potential that I'm applying, I'd have a certain loss across that. Now, this problem of uncontrolled loss was more of a problem in the past than it is now. So it's interesting, actually, because when you think about what a potentiostat does, it was really a device that came before we had electrodes like this. Now, the reason I bring this up is, in a minute, I'm going to say that E loss is an uncontrolled parameter. But I realize that nowadays, like, we have electrodes like this, that many of the uncontrolled parameters are actually controlled, because this effectively, a screen printed electrode is an electrochemical cell. But the potentiostat is meant to control the problem of E loss having many contributions to it, and these are being slightly, let's say, uncontrolled. So let me go through that a little bit more. So the potential at the working electrode suffers from an uncontrolled or undefined losses, and this is the problem at the potentiostat. And these variables for that sort of uncontrolled area of the electrodes, and I would actually argue that's why screen printed electrodes are actually quite interesting, because the area of electrodes is actually quite fixed. Material of the counter electrode, well, the material of the counter electrode, at least when you're using screen printed electrodes from ZP, for example, is not uncontrolled, because actually it's fixed. Distance between the working electrode and counter electrode, this is often an uncontrolled parameter in people who are not using screen printed electrodes, because, you know, they get a certain capability of setting up the electrode or setting up the electrochemical cell any way they want. But on a screen printed electrode, that is not an uncontrolled variable, actually. Conductivity of the solution. So the conductivity of the solution, I don't think this is an uncontrolled variable. In my world, people use a lot of saline-based solutions, and the sodium chloride concentration is about 135 millimolar. So it's quite conductive and not necessarily a variable. Now there is an interesting variable here, which is the condition of the counter electrode. I say it's interesting because, in fact, I mean, these screen printed electrodes, they're often designed to be kind of used once. So the counter electrode's often not got a lot of variable in it. Now this is true, this is something that's true. The current passed, so you can have a E loss that's proportional to the current pass. Now what I would say is the currents when you're using screen printed electrodes at most maybe like 10 microamps. So that's 10 to the minus 6. So you could understand that even if you had a resistor that was a kiloohm, the potential that you just dropped was 10 to the minus 6 times 10 to the 3, which is 10 to the minus 3. That's 1 millivolt. So some of the sort of historical reasons for having a potentiostat were because, in fact, potentiostats predate, I would say, screen printed electrodes and a lot of this sort of low current electroanalytical chemistry that we're now doing. Out of interest, potentiostats, I think, first appeared in the 40s. And I think that they were actually invented at Leicester University in the UK. Still trying to, I don't know if I'm trying to figure it out, but over the time I'll sort of, I will sort of understand it a bit better. So in fact, all these variables were considered to be true variables, and therefore people would suffer from reproducibility. And how did they solve this problem? And I say that this reproducibility problem has actually gone away quite a bit in my world because, in fact, of potentiostats like the Sensi All that I have with me, and also because of the screen printed electrodes. But the solution that was historically applied was that we have a potentiostat and we put a reference electrode in there. And this is now coming towards the question of the person, which is, if you've got control of the potential of the working electrode, why do we still get IR drop problems? And so what the reference electrode does is it's truly trying to measure the potential at the working electrode, and it's basically trying to compensate for all these E losses. These E losses are not really part of the measurement, and so we apply an E total, but it's the potential at the working electrode that we're actually controlling. As I say, these are very defined pieces, like screen printed electrodes. This is a screen printed electrode from ZP. They're really defined. So many of those variables actually are not so much variables as you would once imagine. So it actually reduces the need for the idea of a potentiostat. We still use potentiostats as ZP. I mean, we sell and make potentiostats, but it's an interesting point when I answering this question about actually, the idea of needing a 3 electrode system versus a 2 electrode system, it becomes less critical when you do have a very controlled electrochemical cell like a screen printed electrode. So let me dive into the real question here, which is, why are we still suffering from IR drop if we're using a potentiostat? If we sort of zoom in on what's happening between this working reference and counter here, we've got this working electrode in ionic contact with a counter electrode, and I've shown in between them that we have what's called the Randall's circuit. Now we're measuring the potential at that working electrode by having a reference electrode. So this is the reference electrode here, this is the working electrode here, and this is the counter electrode here. Now we're measuring the potential at that working electrode using a reference electrode. So I've just sort of shown that in here. So now the Randall circuit has the charge transfer resistance. This is truly the charge transfer right at the electrode between the redox molecule and the electrode. We have something called double layer capacitance. This is the ability of the electrode and electrolyte to essentially store charge. And then we have the R sol here. This R sol is, when you talk about IR resistance, this is the culprit, let's say, this solution resistance here. So what you have to understand is we have a potentiostat, but in this particular configuration, we've got that reference electrode, within some millimeters of the working electrode. So it's pretty close, but there's still some solution in there. And so the closer we can bring the reference electrodes to the working electrode, the smaller this resistance R sol is, but it's always there. So the potentiostat, I know everyone says, I'm controlling the potential at the working electrode, but you're losing a little bit of potential across this electrode here. The closer you bring the reference, then the less of a contribution this is. But there's physically, we don't have the control required, the physical control to actually bring it so close that, there's a point where you bring it so close that you're touching it. So we can bring it within some millimeters by the way we manufacture, but there is still some solution resistance. Now, this resistor, by the way, is proportional to the resistivity of the solution. I'll just get rid of myself for a second. And so if you make up a saline solution, the resistivity can be quite low. The length, so the closer we make the reference electrode to the working electrode, length decreases and therefore the resistance decreases. And this is an interesting one actually, area. This is it's a little bit tricky actually. Well, I suppose it's not a little bit tricky. If that working electrode is essentially bigger and we're passing ions through a fairly large cross-section of liquids, then you could argue that the cross-sectional area is larger. But I'm a little bit shaky on because you do get benefits from making microelectrodes, and the benefits you get from making microelectrodes is the current's very small. But let me just run you a quick back of the envelope calculation. Typically, when we're using these screen printed electrodes, our solution resistance is actually 200 ohms. The IR drop that we get across this solution resistance is I times resistance. Now, a typical kind of current that one might pass in at least a screen printed electrode type assay may be 1 microamp. Now, 1 times 10 to the minus 6 times 200 is actually 2 times 10 to the minus 4. What does that mean then? That means that we're really only dropping a potential of 0.2 millivolts. So I think you can appreciate that the IR drop, at least in the world of aqueous electroanalytical chemistry that we do, is actually a really small phenomenon, because the electrodes are very close to one another, the currents passed are very small, and the solutions are quite conductive. Let me just go on to here. Now this gentleman had a second question, which is, I think just, in EIS, you can actually measure this solution resistance. So I'm showing, this is data found in a paper. And if I look at their Nyquist plot, so they're showing their data in a Nyquist plot here. There's a kind of an imaginary semicircle here. And it intercepts the axis here at about 250 ohms. So their resistance here is actually 250 ohms, which is not too far off of that kind of 200 ohms that I was using for my back of the envelope calculations here. So EIS doesn't compensate, doesn't eliminate solution resistance. It tells you what it is. Now, if you had a whole series of experiments and they all had different solution resistances, you could basically subtract the solution resistance and get rid of it as a variable. So EIS doesn't solve the problem, it just tells you how big a problem you've got, let's say. And in fact, when I look at this, see that the solution resistance is 200 ohms, but the what's called the RCT, the charge transfer resistance, is more like, I'm just kind of estimating here, is on the order of sort of 1500 ohms. So 200 ohms versus 1500 ohms, that's about it's about 12%-ish of the total, let's say, impedance. So I'm not saying it's super small in this particular case, but actually within our own data, we've often got a lot bigger charge transfer resistance. So the solution resistance is actually sort of minuscule compared, let's say, to the total resistance of the electrochemical cell. So in order to answer this person's question, the original question was, if you've got a potentiostat and it's got compensation, why do you still have a solution resistance? And it's because there's still a small amount of solution between the reference electrode and working electrode, and we're actually dropping some voltage over that resistor. But in my world, because the gaps are small, the solutions are quite conductive, and the currents are small, actually we don't have a big IR problem. But I can understand in more higher currents, larger electrodes, less conductive materials, then you do have a problem, and the potentiostat will, the raw signal will suffer from this IR drop. If you want to know what your IR drop is, then EIS is quite a good way of actually being able to deconvolute and actually find out what that IR drop really is. And looking at the Nyquist plots, you can kind of see where it intercepts the x-axis here, or the real component, and that will tell you what the solution resistance is, RU that is. Actually, I've mislabeled this, and I really apologize for that, because I realized I've put here 250 ohms. I should have put that arrow here. My real apologies for that. Just noticed my mistake now. So that's what is the intercept, and my apologies. 250 here is measuring to 250 here. But it is a diminishing problem, I would say, these days, because actually, at least in the world of electroanalytical chemistry, a lot more people are actually using screen printed electrodes, where all those variables that I was talking about earlier on, that the potentiostat was developed to overcome a series of variables. But those variables were when people were often making their own electroanalytical cell. You know, they have an electrode in there. It may be a carbon disc electrode, a gauze electrode as a counter electrode, and then they would have a reference electrode in there as well, and they would place them all themselves. And then you could have quite a lot of variability. But obviously, when you've got electrochemical cells that are printed like this, then the problem is really kind of diminishing. Question number 3, making an aptamer biosensor. At ZP, we make a lot of, well, we do a lot of work on aptamer biosensors. I think aptamers are actually, I think they're a useful group of molecules. You can sort of design them, make them specific to your target, and we do this quite a bit. And these days now, people are also allowing to have a redox probe on the aptamer, so that when the aptamer then binds with its target, so here's an unbound aptamer, and we could read it by voltammetry. I suppose it's probably worth saying that a lot of the time at ZP, in fact, here's my electrode again. I'm just going to go into my app. I just want to scan this particular QR code. So now I'm into square wave voltammetry. SQV. Continue. And then I've got all these settings, and I can basically do a square wave voltammetry kind of measurement. In fact, I've still got the ferricyanide solution on there. So I quite like square wave voltammetry as a methodology for reading aptamers. In this particular conformation, when the target binds, we actually end up moving the redox molecule essentially away from the electrode, and so we get a diminishing signal. You can also design it that the conformational change means that you bring the redox molecule to the surface, and that's quite good, because then you get a kind of increasing signal, let's say, with binding. So it's a kind of positive change rather than a negative change. Now, something that I have put a lot of videos out about, lots of aptamers are actually built upon gold electrodes. At ZP, we have talked about activating gold electrodes and how to build an aptamer biosensor. So this link, I don't want to go back over old ground, but I'll put that link in here. And it's probably worth saying that the way we kind of tend to, the first thing to probably worth saying is in the previous link, we take a lot of effort to activate the gold. When I say activate the gold, it's a sort of slightly fancy way of saying just clean it. And we actually just clean it just before use, actually. We kind of activate it and then put these thiols on there. But we don't just put the aptamer down there. We do it in a two-step process. We put the aptamer down, and then we'll put a spacer molecule like MCH. Methyl, that's not methyl, MCH, mercaptohexothiol. I'm not getting that right. But we do put a short chain thiol in there to space the aptamer out. But we do it in a two-step process. We put the aptamer down, then we put the we put the aptamer down, then we put the spacer molecule MCH, for example, down. Then we can kind of essentially read the assay. But sometimes, earlier on I showed a conformational change to read the assay. Sometimes we'll use an external redox molecule like ferricyanide, for example, to read the binding. Now, in this particular case, so I'm going to get more specific into this person's problem. They have a small molecule binding to this aptamer. The fact that the molecule is small does make this much harder to do, Because if they had a big molecule, let's say, or larger molecule, a macromolecule, maybe if I was being more scientific about it, they could actually check whether they got binding, not through the conformational change, but they could actually bind the macromolecule to the aptamer. That would block the surface, and then they could use essentially a ferricyanide-based signal by using square wave or cyclovoltammetry, as I've been demonstrating on this particular potentiostat. So if I was going to do cyclovoltammetry again, I could just come over here, square wave, cyclovoltammetry. So they can just they could interrogate whether they just got binding, not having to rely on the conformational change of the aptamer, but actually just using a redox reporter. But their molecule is quite small, so I actually think that I would bet it's not going to work, because there's basically too much of a little change on the surface to actually really work. So they've actually got a, I don't want to say it, it's a bit of a tricky problem, to be honest with you. I'm not sure I've got the entire solution, and don't think I've got the entire solution to this. Something that's come out from the conversation is that something that they do, and you should all remember, is that most aptamers actually come as a disulfide. So make sure that you do actually reduce the disulfide before you put it onto the surface. We definitely do that. We do it in a large excess of TCEP. We clean the gold electrode just before use. They clean the gold electrode just before use. So I'm basically ticking off that everything they do is everything that we do. Do they put a spacer molecule in? They put a spacer molecule in there to make sure it's not overcrowded. They use MCH. We use MCH. Are you following the steps by voltammetry? And they were able to show me that they're following the steps by voltammetry as well. So a pristine electrode, a aptamer electrode, and then an aptamer electrode after the addition of spacer. And I don't mind that their voltammetry has kind of, it's, when they had the aptamer, the surface was very blocked, and when they added the spacer molecule, the surface became less blocked. But I think that's a fair, it's okay, because I think that actually replacing the aptamer with MCH or spreading the aptamers out a little bit, you will actually move the voltammetry slightly from an aptamer only blocked sensor to a more, I don't want to say pristine gold electrode, but the direction in which their voltammetry goes after the placement of the spacer, I think, is perfectly reasonable, actually. I got a super strong suspicion that this person's aptamer is, I'm not suspicion, you can see it in their data, their aptamer binds to the surface. Their problem is whether their aptamer actually binds the target, and on binding the target, does it undergo the conformational change? And they suggested, you know, they're thinking this through the same way I would. They said SPR, surface plasma resonance, may be a way of doing it. And I agree with them, though. The problem is the molecule is so small that they're trying to bind. It's only about 500 Daltons. Just not going to see it by SPR. It's the same way you're not going to see it by that ferricyanide. At least with the ferricyanide experiment, you could try it. But I'm not holding up a lot of hope. And I suppose it's a tricky one. It's almost like if there's somebody in the lab that's doing another aptamer assay, and you're able to do their aptamer assay, but you're not able to follow the aptamer assay out of the literature, it could be the literature that's actually not reporting 100%. So with this one, I followed their steps. They do exactly what we're doing, and I'm left thinking it's actually not so much the binding of the aptamer, but the aptamer itself in actually detecting that molecule. So question number 4, detection of I can hardly say this, catecholamines. Coming from a guy with a background in chemistry, catecholamines. Okay. The first thing they're doing is actually putting some P.PSS down on the electrode. P.PSS is a sort of 24-year-old piece of, let's say, science. You can do electropolymerization. It's quite easy to do, and you can kind of do it by something like cyclovoltammetry. Again, you know, the tool, the potentiostat that I have in front of me, perfectly capable of doing this kind of work. So they're putting that down. Now, what they're getting is delamination. Now, the reason you can kind of get delamination is that they've got a gold electrode. It's super smooth, I suspect. Now, I can tell it's super smooth because actually I'm feeling that it's actually quite shiny. So there's no real reason why P dot should adhere to that surface. There's no reason why. If I had a mirror-like finish, and it was conductive, and I could therefore electropolymerize P dot PSS on top of it, there's no reason why it should then stay on that surface. What would help is if it's a thin layer, but these are quite dark layers when you look at that. So when they've basically got a thicker layer, and as it then, let's say, dries out, you kind of get these internal shrinkages, and the internal shrinkages then can lead to this kind of breakage. So it's very thick. If it was thinner, it would probably adhere better. And we do a lot of electropolymerizations ourselves, but we do it on our kind of gold electrodes, and I suspect that our gold, well, you can almost see it, is duller than their nice shiny gold. So we've got a rougher surface, and with a rougher surface, the P dot PSS can actually probably literally grip the surface, because there's nooks and crannies that the P dot can polymerize in, and so it's anchored on the surface by almost like a physical attachment. But there's no reason why the P dot PSS should stay to the surface with gold. And especially the thicker it is, the more likely it is actually to come off. Whilst making this slide, I realized that you could, for what they're doing, they might as well just use carbon as well. So they didn't have to use gold. Sometimes people use gold because there's a precedence in the literature for it. But in fact, they're probably following papers from University College San Diego, and they tend to use a lot of gold, but carbon would just do the job just as well, and they probably have a better adherence between P dot and gold, because you're going to have, P dot and carbon. Carbon's rough, and there's also a sort of chance for sort of pi-pi interactions, so you may get a stronger binding to carbon. You can sort of see my point here. See this? So they've done some galvanostatic polymerization at different current densities, and the higher the current density, the darker and thicker the polymer, and then the darker and thicker it is, the more likely it is to delaminate. So that kind of slide I put up earlier on about these internal forces kind of shrinking and pulling the material off the surface, they get least evidence of that on their low current density, their thin film. Medium current density, let's say, less evidence of delamination, and then the high current density, boom, off it comes. What they're ultimately trying to detect is these neurotransmitters, these catecholamines, and I just did a quick bit of search on this, and actually I found quite a lot of precedents for doing this on carbon electrodes. So if I was trying to make a quick, I'm just making this up a little bit, but I was trying to make a quick saliva test for catecholamines. Again, I could take one of our electrodes, I could put a solution of that catecholamine on there, I could use the square wave voltammetry, and I can essentially run a quick assay using the potentiostat. So I think carbon electrodes are actually, I always quite like carbon. This is a sort of a slight sidebar comment actually. I quite like carbon because it's very low cost. We can sell carbon electrodes, for sort of, just euros, let's say, or, less than €1 on some of them. Whereas gold as a material is 24,000 times more expensive than carbon. So it's never going to make for a low cost sensor. Now in this particular application, the sensor might not need to be low cost, but personally, especially in the lab and the R&D, carbon, when budgets are limited, carbon's probably a better material. They didn't particularly need gold. Now they're a little bit concerned that they got this kind of peak also on their gold. And I did a little bit of research on it, and this peak actually appears, a lot of bare gold electrode work that I can find, this peak does appear. I don't want to speculate, 'cause I'm not entirely certain what it is, but I have found it, and I suppose I am speculating a little bit, because I did find some partial evidence that actually there might be some copper in their gold. I'm sure they're not intending it to be, but they actually, I wonder if there is copper. Actually, they may have some copper in their gold, is the quick answer to it. What I want to say is, if you're doing biosensor development and you've got a project which has two sort of mixed objectives, in this particular project, they're developing an electrode, and then they're trying to develop an assay upon it, and they're doing it at the same time. they've mixed these two things. So you've got really two aims. I want an electrode and I want an assay upon that electrode, but you've mixed it. You're doing two things at once. Split these things off. Split these things apart. This is the strategy part. I don't think you will get this on many other channels on ZP because there's no really anyone else talking about, let's say, commercialization of electrochemical sensors. Split the assay apart. Work on the gold electrode. You've got a PhD, let's say it'll take 3 years, so work on your gold electrode. And you've also got assay and functionalization that you want to develop. Work on low cost, easy to obtain electrodes that you can just do, destroy, make mistakes. The problem is when you make a bespoke material, you're making it or your colleague is making it. There's reproducibility problems, there's quality problems. If you really cost it out what it costs you to make those materials, it's actually quite expensive. And you've probably got a limited supply, so you can't really do enough of the chemistry and electrochemistry work that you need to do because the electrodes are actually limiting you. So actually split these two things apart. Work on low cost, easy to obtain electrodes for the functionalization and the assay, and then also you can also then do your development, but you don't couple these two things together. When you've done all your, at the end of your PhD, let's say the end of the second year, you can bring these two things back together again. But otherwise, you're constantly trying to develop an assay and functionalization upon a piece that's very variable. So big strategy. If you're trying to develop new electrodes with new functionalizations for a new target molecule, split the project. Do some work on low cost, easy to obtain electrodes, and in parallel you can do the other stuff, but you can't have them connected because you're in the end you've got a variable thing, which is the electrode that you're trying to fabricate, and that's variable, and then you're trying to build an assay on top of it, and you've got variability on top of variability. Split the two things off. Question. So let me just do a summary. Characterization of third-party electrodes. If you've got cyclophotometry and it looks very stretched, it may be just connection problems. Potentiostats do compensate for the uncontrolled losses due to the counter electrode, but in fact there's still a slug or a thin film of liquid, and you still will get IR drop. In my world of electroanalytical chemistry or screen printed electrodes, it's actually no problems anymore. But making an aptamer sensor, I generally think this person is binding their aptamer to their surface. Your work reflects our work. Our work reflects your work, but you're not getting a signal on binding. I suspect it's the aptamer itself. Building a biosensor for catecholamines. You can use carbon as well as gold. Your P.PSS is peeling off because there's no real reason why the P.PSS should actually adhere to the gold. It'll probably adhere if you made it a thinner film, or maybe if you went to a carbon electrode. I think carbon's actually not a bad material. And in your program, you're mixing two things. You're mixing fabrication of the electrode with building value on top of the electrode. You need to split those two things and then bring them together at the end. And that's more of a strategic comment. None of these questions were from people who were at this moment using ZP materials, but if you are a ZP client, or user of materials, you can see how much effort we actually put into just answering questions. So if you have any questions of ZP, essentially don't hesitate to reach out to us. I super hope that people will actually use our screen printed electrodes and our potentiostats. They're super good. We use them. I mean, they're actually beautiful, to be honest with you. But if you have any questions of ZP, again, don't hesitate to reach out to us. Okay, thanks very much.